and this will tie in with the demos I'm going to do after this slideshow, and with the exercises that we'll do, kind of lab session where you'll do it, and then I'll confirm whether or not you're right or not, or how you might do it if we need to. Okay, I got a note there. I need to increase the volume a little bit. Hang on a second. Let's see if we can do that. Okay, I can push it up here. Okay, how's that? Can you hear me better? That is the input. Yes. Hopefully that helps a bit. Okay, so let's take a look at this slideshow. Okay, so we're gonna to reprise what I just said. We're gonna identify when to use the t-test and when to use the z-statistic. We're gonna understand what a single sample t-test, what a paired sample t-test is, and what independent samples t-test. There's two forms of that. One where we assume equal variances between the two sample groups that we've taken, and another where we don't assume that the variances are equal in the two groups that we're comparing for their mean. So we're going to take a look at each one of them, and we're going to take a look at, also maybe we'll throw in how confidence interval kind of ties into all of this stuff, especially with single sample tests. Maybe not so valuable when we're doing two sample or paired sample. Maybe paired sample also might be valuable for that as well. Okay, so let me get this to advance, assuming it hasn't crashed. There we go. Okay, so let's talk about a single sample confidence interval. We're taking a single, let me just check at the end of the session, if we have time, I'll go back over some of the stuff. And by the way, question number 16 on 5B, we went over that last night. That'll be posted on YouTube tonight, so you'll be able to take a look at it. It's at the very end. It's the last problem that we talked about. Okay, so review sessions. Okay, review during that review session. Okay, so now let me get back to this. I'm a little. I'm trying to do too many things at once here. Okay, here we go. So, single sample confidence interval. Okay, in this case, we don't have any idea what the mean of a population is equal to. In the first part of this, we're going to assume we know what the standard deviation of the population is. That's kind of a weird construct because normally we're not going. If we don't know the mean, we're also not going to know standard deviation of the entire population. But just to demonstrate that if we know the standard deviation of the entire population, we understand fully the probabilities of getting a value below, above, or near certain distances from that mean for that population. We understand that we can construct a confidence interval that really means something. In most cases, though, we're not going to know that, and we're going to have to depend on the standard deviation of the sample that we took in order to estimate the standard deviation of the population. Introduces a bit more uncertainty, so we have to make accommodations for that. One accommodation could be just make the sample size really big, but often that's not practical because it costs money to make a sample big. Often we don't have the resources for that. Okay, so let's see, how would we handle calculating the confidence interval? Well, as you know, we calculate the confidence interval if we know sigma by the mean of the sample that we took, x bar, plus or minus the z value for the alpha that we are willing to accept, the probability that we would miss the mean within the interval that we create, the population mean within the interval that we create. So alpha is equal to 0.05. That's usually what we choose. We could use 0.01 to be 99% confident that we captured the mean. We could use 90% confidence and use 0.1 in order to be 90% confident we captured the mean. And that would make our confidence interval a little bit narrower. But often we use 0.05. The nomenclature they're using here is just alpha over 2, which is 2.5%, 0.025. And they use that to describe either tailed, the amount of uncertainty at the low end and at the high end. So when you add up both tails, that alpha over 2 is alpha, which is 0.05. Okay, so don't be confused by that. Very frequently you see that nomenclature, but that still means we're going to use, it's still going to be a 95% confidence interval, not a 97.5% confidence interval. So, okay, so what are we going to use for that formula? Confidence interval is going to be equal to the mean of our sample plus or minus some margin of error that is based on the variability in the population, sigma, and the sample size that we took. And it's also based on knowing sigma, knowing how wide that interval has to be to capture 95% of the possible samples from that population. Okay, so in this case, Z is going to be equal to 1.96. If we were looking for 99% confidence, we'd be using 2.58. If we were looking for 90% confidence interval, we'd be using 1.64. And all this, as we mentioned before, all this comes from the Z table, right? That is the standard normal distribution table. Or we can also look it up on Excel, get the same value as the value in the table. So Z is going to be 1.96 times the standard deviation of the population divided by the square root of the sample size. Z is 1.96, and sigma is whatever is fed up population, and the sample size is whatever we choose. So if we wanted to test how far, whether or not the mean of our population that we've taken the sample from is equal to the mean of another population that's known. Ours is not known. All we know is our sample mean. We don't know our population mean. We want to compare that to another population where the mean is known. We can actually, instead of this, turn it around and calculate, rather than using 1.96 calculate confidence interval, we can use a Z statistic, the amount of distance in standard errors between the mean of our sample and the mean that we know from the other population. We can see if that distance is wide enough for us to be 95% sure that the means of the populations that we're dealing with, the mean of the one we got the sample from and the known mean, are different enough to say we're 95% sure that those two means are different from one another. So how do we do that? We calculate a Z statistic. The Z statistic is going to be equal to the number of standard errors apart, just like a confidence interval is 1.9 standard errors to the left and 1.9 standard errors to the right. That's how we get our margin of error. So our Z statistic, we're going to want that Z statistic to be at least 1.96 so that we're sure that the mean that we're comparing our sample to is far enough away that the likelihood of getting that mean result that we got from a sample is less than 5%. So we can say that those two means are different and still have that 95% confidence. So X minus mu, whatever mu is, that's the mean of that we're comparing it to, over sigma over the square root of n. That gives us a number. Okay, so that might be, if there's X bar and mu are close together, that Z value might only be, say, 1.1. Well, that they're too close together for us to reject the null hypothesis and say that the two population means are different. However, if that turns out to be 2.5, 2.5, we know that we've exceeded the 1.96 Z score, standard errors apart, that we need to be more than at least 95% confident and have 5%, less than 5% chance of being wrong if we say that those two means are different from one another. One case we're calculating a confidence interval. The second part here, we're calculating a Z statistic and comparing it to what we're going to call a critical value of Z, the value of Z that we need to exceed in order to say that the two means are different from one another. Later on, we'll be talking about that in terms of rejecting the null hypothesis or failing to reject the null hypothesis. Okay, so now what happens all of a sudden? Now, if we don't know what sigma is and we're forced to use the standard deviation of our sample as a stand-in, okay, well, it's the same idea. The confidence interval for a single sample is going to be X bar, our mean, plus or minus our margin of error. Our margin of error is going to start out with the standard error, S over the square root of n. We substituted that for sigma, so a little bit more uncertainty there. And we're going to multiply that by not z in this case, but a value called t for the t distribution. That t distribution, the same thing, alpha over 2, but notice that there's a degrees of freedom down there too. That depends. The certainty with which we know that we're estimating sigma is going to be impacted by the sample size. We have to make up for that in the t statistic. So that number of degrees of freedom, that's degrees of freedom is basically just a sample size minus 1. So that degrees of freedom, bigger sample size is, the closer that value of t is going to be to 1.96. The bigger the sample size is, the more degrees of freedom. The smaller the sample size is, the bigger that t value is, the more different it's going to be than the z value. And why is that? Because it has to make up for that extra uncertainty. It makes our margin of error bigger, so it makes our confidence interval wider, making up for not knowing the population standard deviation sigma, and also for the sample size if it's a small size. If it's a very small sample size, that t value is going to be much bigger than z. If it's a very big sample size, it's going to approach the value of z, 1.96. So that's how we're going to calculate a confidence interval if we don't know sigma. Now, just as we did before, we can use the same way of handling this data to actually calculate a z statistic. Hold on just a second. Let me just keep talking until I finish this. A z statistic in order to calculate whether or not our two means are far enough apart. So that z statistic, again on top, is going to be x bar minus the mean that's known over, instead of sigma, a standard deviation over the square root of n. Now, that value, had it been t, right, had it been z, it would have been 1.96, but now it's going to be t instead. So the t value that we're going to have to compare it to is going to be a bigger number. So let's say that comes out to be 2.0. Well, if our sample is very small, the critical value of t that we need to exceed from our table might be 2.3. So if we get a z value of 2, had we been working with sigma, we would have been able to reject that null hypothesis because it's bigger than 1.96. But now we failed to reject that null hypothesis. We don't have enough evidence that the two means are different from one another because we haven't exceeded the value of t that we need to exceed. So we got two values of t. We got the t we calculate, they call it z here, but it's t calculated. And we have the t critical that we get from the table that's specific for that sample size. Okay, so I'm getting a message that my volume is not good. I don't think I've changed anything here. Is that just one person, or is that a lot of people? You guys okay otherwise? Remember, it's recording also. Yeah, check your own check your speaker volume on your end too. Maybe that's the problem as well. Okay, so yeah, hopefully it'll record well too. Okay, so you'll be able to get that as well. Okay, so now that's great for single sample, right? So we have a mechanism now for comparing a single sample, the mean of a single sample, to a known mean of another population to see if the means are different between those two populations. Okay, well, most of the time we're not dealing with a single sample. Most of the time we're comparing one population to another population. We may be comparing blood lead levels to children that live in older housing, the blood lead level of children that live in more modern housing. For instance, that's two different groups. We're going to sample each group. We want to know what we really want to know. What really we're after is what is the mean blood lead level for all the children in all the older housing versus the mean blood level for all of the children in all the modern housing, right? But we don't have the facilities to go out and test every child in both of those types of housing. So we're going to rely on it. That's where statistics comes in. We're going to rely on a sample to tell us whether the means of this population is equal to the mean of this population. We're never going to know for sure, right? We're only going to know to a certain level of confidence, right? If the two means are the same or different, because the only way to know for sure is to sample every child in both populations. So let's give this a try. How is this going to work? Well, there's a couple of ways that we could look at this. One is if they're independent samples, like I just described. The other way is to see if they're paired samples. Paired samples are a little bit different. Okay, for instance, that might be the situation if we took a child that was in that had lived for a year in older housing, but now had moved into newer housing and had lived in newer housing for a year. And then we also looked at children that had lived in older housing, newer housing, and then moved into older housing, and look to see whether the what the blood lead level of children that went what the blood lead level was for each child before and after they changed housing. So what we're looking for is whether or not their blood lead level was higher in the older housing versus the newer housing. So for each child, we got two readings. We have reading when they were living in the older housing and a reading when they were living in the newer housing, each one for, say, a period of a year at least, right? So, but it's the same child, right? So each one of these childs, we might have 50 subjects, but for each subject, we would have two values. What their blood lead level is when they're older housing, what their blood lead level is in newer housing. So what we're really looking at is there a difference between the two? So I would take each one of the 50 pairs of numbers, subtract each value. So let's say moving from the first subject, the first child, moving from older housing to new housing after a year, their blood level had come down 1 microgram per deciliter. And another child had gone up 2 micrograms per deciliter. And another child, depending on which direction that they moved, of course, right? So our expectation is that if there was no difference in the housing that they lived in, we would expect all of those differences to average to zero. In other words, the only reason they would be, if it didn't matter whether you lived in older or newer housing, then you would expect no difference. We never really get no difference, right? You test today, you test again tomorrow, it's going to be a little, even your blood sugar, you test it today, test it tomorrow, it's going to be a little bit different, right? So we wouldn't expect it to be the same, but we would expect the differences to average out and the average difference to be equal to zero. Well, what does that sound like? It sounds like we're ignoring the two sets of data, two samples that we took from each child, and only looking at the differences. So we're going to take all of those differences, use that as our sample, and compare it to the value of zero. And now we're going to use the z-test or the t-test in order to predict whether or not we can reject the null hypothesis that the difference in housing had no effect on the blood lead level. In other words, the mean blood lead level for these children was equal to not the same as zero, either not the same as zero or the same as zero. In other words, can we reject our null hypothesis and say that this average is far enough from zero? In other words, that's a t-score that's big enough or a z-score that's big enough for us to reject the null hypothesis that there was no difference, that it was really just zero. Each way you looked at it was equal to zero. So at any rate, so that is a paired sample test. Notice how specific that is, right? That's specific because you use the same subject before and after, right? So, and you looked at the differences. Okay, so you round up at a single set of data, a single sample, not really two samples. So you can see that it's a single sample test, really. Now, independent samples tests are two different populations. That's the first one I described. Children in older housing, children in newer housing, you want to compare the means of those two populations. Those are two separate samples. So now when we take a sample, it could be same, say sample size of 25 from one group and 25 from another group, randomly sampled. Or it could be a bigger sample, it could be a smaller sample. Doesn't even have to be the same size sample. In fact, very frequently it's not same size sample because you might have 50 people in one group, 50 people in another group. Somebody may drop out. You may not be able to get a good reading. The sample may drop on the floor in the lab. Who knows what might happen? So the sample size could conceivably be a bit different. Okay, so, but we can calculate means for the X bars for the children in the older housing, the X bar for the children in the newer housing. Now we have to compare the two of them. So how do we compare them? We take our equation. We take our equation. which is going to be X bar for children in old housing, minus X bar for children in newer housing, the difference in the two means, and divide it by the standard error. How do we calculate standard error? Well, we use the standard deviation over the square root of the sample size. Well, now we're confronted with two issues. One is, what if the standard deviation of this group is 1 microgram per deciliter, and standard deviation of this group is 1.5 micrograms per deciliter? Which one do we use? Do we combine the two of them? Do we pool them together? How are we going to handle that? Well, what if the sample size here is 49, sample size here is 75? How many degrees of freedom are we dealing with when we calculate our t-value, right? So there's a number of issues that you have to deal with when you're doing independent samples that didn't come up with paired samples or with single sample tests. And we're going to take a real close look at that when we start working with some examples. Independent samples, birth weights, unrelated boys and girls, laboratory results, two different participants in a clinical trial, comparison of household health care costs in the United States versus Canada, two different groups, two different sample groups. Paired sample or dependent measurements, difference in birth weight of twins, right? So in other words, you're not going to compare all of the 25 kids to 25 kids. You're going to compare each twin to their sibling, right, and get a difference, right? Pre and post laboratory results for people in a clinical trial. You're going to measure something before, measure something after, and then you're going to be looking to see if the difference is different than zero. Ocular measurements in the right eye and left eye. Again, same subject. Stress measurement scores in twins or housewife pairs. Measurements from two methods of conducting an assay on a single patient. Basically, all of those were kind of a way of doing that. When to use paired sample measurements, here's some examples. Average, which of these are paired measurements? I'll leave you to tell me that. Tell me that which of these are paired measurements? Okay, 1, 2, or 3. Which one's a paired measurement? It's only one of them. 2, not 2 and 3, just 2. Right? Anxiety levels are two groups, one with and without an intervention. If it had been the same group, right, the same group before and after intervention, in other words, same people, it would have been 3. But in this case, only 2 is the only one that has the measure as the same person before and after an intervention. Yeah, it's kind of a little, that 3's worded a little bit sneaky. I have to agree with you that. Okay, now again, here's our description, single sample, our paired samples. See a difference minus that difference of 0, that silly little delta there with that null is just really just 0. You're comparing the mean difference to 0. Okay, single sample test, where we calculate confidence interval, paired sample test, the way we calculate confidence interval for the difference from 0. So it'd be the mean difference plus or minus our t-value, which is based on our sample size, times our standard deviation for all of the differences over the square root of the sample size. Okay, so let's take a look at the independent samples test. For means, okay, so this is a cell phone study. The cell phone use while driving impair reaction. Whoops, sorry about that. Okay, let me move this out of the way so I can read this. Experiment students used a machine that simulated driving situation. At irregular intervals, a target flashed red or green. Participants were instructed to press a brake as soon as possible when they detected a red light. For each subject, the experiment analyzed their mean response time over all the trials. 32 students were randomly assigned to the cell phone group, and 32 were assigned to the control group. Okay, so does that look like a independent samples test or a paired samples test? Two different groups. One group was assigned to cell phones, the other group to the control group. Had they just gotten 64 students and had each one of them do both sets of readings, one with a cell phone and one without the cell phone, and just looked at the difference for each student, that would be a single sample test. Okay, here's the results of the means. These are box plots, so that's the median. The median is 58.585 milliseconds. Cell phone, 533 without the cell phone. Sample sizes, So now we need, if we really wanted to test, now remember, this is our samples. This is our distribution of samples down here. It looks like it took the kids with that had the cell phones longer to stop to react than it did the kids without the cell phone. But is that true for the entire population of all teenagers that have or don't have drive or don't drive with or without cell phones? Well, we don't know that. We need to know the variability here and compare them and see if their means are far enough apart for us to reject the null hypothesis that there's no difference between the two of them. So we need to calculate that. So we have a treatment group, we have a control group. Basically, the cell phone group is the treatment group. Population means, or mean for the control group, mean for the treatment group. We focus on testing the null hypothesis. The null hypothesis, in this case, if I don't know which way it's going to work, the null hypothesis could be the mean of the control group is equal to the mean of the treatment group. In other words, no difference in reaction time. Or you could call the null hypothesis the difference between the two of them, the control and the treatment group, is zero. The average difference in means is equal to zero. Both of these are a way you could phrase the null hypothesis. I suggest, to avoid confusion, that you stick to the first way. It's a little bit easier to interpret. Okay, so we're going to have look for the difference in the means, not the differences in the individuals. Okay, so one sample z-score and a two sample z-score. So what are we doing with, what's the difference here when we do a one sample z-score versus a two sample z-score? Well, the one sample z-score is pretty simple. Difference of the two means over the standard deviation over the square root of n. Our standard error that's our standard error on the bottom. That gives us the number of standard errors apart the two means are, or in other words, the number of z-scores they are apart. Same thing, means same thing. So if we now are going to work with two samples, we got a problem here. One problem is that we got two means, not just one mean, right? So in the top here, the top part's not that hard, because we're looking for the difference in the two means to be equal, for null hypothesis to be equal to zero. So if you look at the way they describe it here, they're saying x bar 2 minus x bar 1 minus the true mean 2 minus the true mean 1. Null hypothesis says that they're equal, those two means. So we can just drop that whole second part out. As soon as we say null hypothesis means that they're zero, we can drop that second part out. So we don't need that. We can drop that out entirely. So it's just x2 bar minus x1 bar. And it's divided by the standard error. Now, problem with the standard error is we don't have just standard deviation divided by the square root of the sample size. Now, we have to calculate the standard error based on two different standard deviations. And in this case, the way we calculate it, this is for not assuming equal variances. So we're going to get into this later on in a little bit more detail. But in this particular equation, they're using the square root of the standard deviations of the first population squared over the sample size plus standard deviation of the second sample squared over the sample size. Now notice that top part is the variance, right? That's the standard deviation squared is the variance divided by the sample size for each group. You add them together, you find the square root. That's your standard error. This is a case where they're telling us you know the standard deviation of the two populations, even though you don't know their mean for some reason. Not going to happen in real life, right? So where do we go from there? Well, let's say that we're going to do a two-sample statistical test, hypothesis test, but we don't know the standard deviations of the two populations because, that's real life. That's usually what happens. So now it's the same thing, except z, it's going to be t is equal to x bar minus mu divided by the standard deviation over the square root of the sample size. So now, if you look, the t unpooled is going to be equal to, and that's unpooled is down here to let you know that you're not assuming that the two standard deviations are equal to one another, right? That's why they say unpooled. You're not pooling them together to get a single standard deviation. Okay, it's equal to, and again, you can drop out that mu2 minus mu1, so it's equal to the difference in the two means divided by the standard error. And standard error, instead of being sigma squared over n2 and sigma 1 squared over n1, it's now the standard deviation from our sample, from each sample squared. And that's how we get our t-score. And again, depending on your sample size. Now we got two sample sizes. How do you, in this case, how do you determine what number of degrees of freedom to use? You have sample size one, sample size one. One could be 10, the other one could be 30, right? Could be a big difference in the sample sizes. So what do you use for a number of degrees of freedom? We'll be getting to that as we work through this. Okay, so two samples, if we pool the standard deviations, the standard deviation, pooled standard deviation, in other words, we assume that they're equal and we pull them together so we get a single standard error, right? A single standard deviation pulled together. This is the formula that we use. Down there is the pooled standard deviation. So the pooled standard deviation is equal to the n2 minus 1 times the standard deviation squared for the group 2 plus the same thing for group 1 over the sum of the two sample sizes minus 2. Okay, if they were 50 each, it'd be 100 minus 2 would be 98 down there. That's our pooled standard deviation. It's basically a weighted average of the two standard deviations. Sometimes we're going to be using that, sometimes not. If you look, the reasoning behind using that is that you're assuming that the two populations have the same standard deviation. So if you look back at the top there, the standard error now is going to be the pooled standard deviation squared times 1 over n1 and 1 plus 1 over n2, and you find square root of that, and you just find your t-value. Again, now, since we know that the degrees of freedom is down there, is going to be 98, we can go to our table and look up what the t-value is for a sample size of 98. Maybe it's like about 2.0 or 1.99, something like that. So that's going to be our critical value of t. So the t you calculate is bigger than 1.99, you can reject your null hypothesis. Let me just take a quick look at the chat box, see if I'm missing anything. You still have to take the square root at the end. Yes, yes. Okay. Except that you calculate this number and then use it in this formula. That's where that's going. That's pooled standard deviation squared. It then goes into this formula here, which this is the actual standard error. This is actual standard error here that you're dividing into the difference between the means, right? It's just that this formula here is what you need to calculate the pooled standard deviation. Okay, so
Professor,
yes.
what is the purpose of pooling or not pooling? Why do we pool samples and why don't we do that?
Okay, well, if you can imagine, if we pool the samples, instead of basing our standard error on 50 values, let's say that we have a sample size of 50 from one group, sample size of 50 from the other group. If I can pool the two of them, I now have a sample. I can base my standard deviation and my standard error on a sample size of 100. It's more reliable if I can pool the two of them. The logic behind being able to pool the two of them is you first have to make the assumption, right? First have to make the assumption that the two groups have no reason to have, even though they might have different means, there's no reason for them to have different variability. In other words, even though men weigh 200 pounds and women weigh 150 pounds on average, there's no reason to believe that the variability in their weights, the differences within the groups, are different for women than they are for men. So that you have to make that assumption, right? So if you can make that assumption safely, right, then you can pool them. You get a more accurate determination, more likely to reject the null hypothesis. But if you can't, not doing that is the safer assumption if you're not sure, right? So we're going to look at how to do it both ways, but for most cases, we are not going to assume that you can pool them. But I just want to expose you to the fact that if you take another course in statistic, and also when we use SPSS calculates it automatically both ways. It calculates it by pooling the standard deviations, and it calculates it by not pooling the standard deviations, right? So you're going to see two lines for the t-test, and you're going to have to say, well, which one of these two lines, which one of these two t-tests should I use? So I need to expose you to this. So in another course I'm teaching, which was pre-programmed, it's all videos that have been pre-recorded. The person that recorded that told the students at the beginning, hey, listen, This whole course, we're going to assume that we're not going to assume pooling. You're never through this course going to assume that you can pool, that the standard deviations are the same, and that you can pool it. We're always going to work with, that you can't pool them, that they're not equal and you can't pool them. So, however, you still need to know about this, right? In case you see it in the future, and then you're going to see it in SPSS when we do the calculations. Okay, so now, if we use a pooled standard deviation, the degrees of freedom is equal to n1 plus n2 minus 2. Nice and simple. If we use an unpooled standard deviation, look at that mess, right? That's what the degrees of freedom is equal to. You'll notice when we do it in SPSS, the degrees of freedom comes up to here the degrees of freedom is always an integer, right? Obviously, because it's just the two of them, the two sets of subject minus 2. Down here, very frequently comes up, almost always comes up with with a, a fractional number, right? So a conservative estimate of the degrees of freedom is the minimum value for n1 or n2 minus 1. Whichever one of these two is less, take that one and subtract 1. So if we had two groups, 50 and 50, the smaller group would be, actually both groups would be 50. We would take 50, subtract 1, and say it was 49 degrees of freedom. That's a conservative estimate. Okay, the only time you're going to use this formula is if SPSS works out that formula for you, which it does every time it does a t-test calculation for you. So you don't have to worry about this. SPSS will, for unpooled standard deviations, SPSS will calculate this value for degrees of freedom for you. You won't have to do it yourself. If you're doing it on a test manually and you're doing the unpooled version, which to tell you the truth is easier because you don't have to pool all this. You can just use this simpler formula here, right? And the degrees of freedom are simple to calculate for that. So chances are, I would probably tell you that on an exam to if I tell you to use the unpooled standard deviation, I would probably tell you just use the minimum here, minimum minus 1, minimum of the two groups minus 1, sample size minus 1. Okay, so what procedure are we going to go through here? We're going to first choose the level of certainty that we need, the level of error, the level of error that I'm willing to accept, the possibility of error that I'm willing to accept. So we want to be 95% certain if we're going to do a study and we're going to want to publish it. We could try to be 99% certain, but chances are that would mean we'd have to stress our resources, get bigger samples, and so on, right? So in most cases, the target is 95% certainty. In other words, alpha, which is 100% minus 5%, 100% minus confidence, it's 100 minus 95 is 5%, right? Is usually going to be 0.05. Okay, so step two, we define our null and alternative hypothesis. In here, they're saying that the difference between the two means, a null hypothesis, the difference between the two means is equal to 0. That's the same thing as describing it as mu c equals mu t, right? You could use either one. Statisticians love this one. Non-statisticians, I think, would be feel more comfortable with just saying mu c equals mu t. Our alternative hypothesis is that the difference is not equal to 0. Or in other words, mu c does not equal mu t. It's really two ways of saying the same thing. Okay, so calculate the test statistic and the p-value. Okay, so how do we do that? Well, the test statistic, we use our formula. We take the difference in the two means. Actually, I think there's data for this around somewhere. Do we have the data for this on any chance? Let's see. Let me pop out here for a moment and see if we have the data for this. Lab exercises, cell phone. I need to say cell phone. Maybe we don't. How about this? That one, these are the ones I'm going to be using. Okay. I don't see it there. You guys look on Blackboard. Let me know if you see it there. I don't know that necessarily it's there. Okay, but at any rate, so we calculate a t statistic. That t statistic comes out to be 2.628. And our degrees of freedom are equal to 56. okay? And our p-value is equal to 0.011. Okay, so what is this telling us? This tells us that these two means are this far apart in standard errors, t-score, in other words. Our degrees of freedom is 56. I can go to the table for t distribution and look up what is the critical value of t for 5% for 56 degrees of freedom. In other words, a sample size of, actually we've been a sample size of 58, right? Because you're going to use subtract 2, right? So what, anybody know what that is? Probably going to be something around like, say, 2.01 or something like that, 2.02, something of that nature. So, since the critical value of t that we need to exceed is only 2.03, and our t that we calculated was 2.68, these two means are far enough apart in terms of standard errors, in terms of z or t score. They're far enough apart for us to reject the null hypothesis. Remember, the key here is the distance between the two means is the two means of our samples, how we decide to reject the null hypothesis. Further apart they are, the more certain that the true population means are different than one another. But we need to have them far enough apart, not in numbers, not in millimeters of mercury for blood pressure, not in micrograms per deciliter for lead levels or something like that. We need them to be far enough apart in terms of standard errors, in terms of the t-score to z-score. So in this case, since it's more than the critical value of t, the t that we calculated is more than the critical value of t, we can reject our null hypothesis. Now, if we did this with SPSS, we could then, we could take these two numbers and put them into a function in Excel, and Excel will tell us what that probability really is. Now, remember, let's say that in this particular case, that the critical value of for this number of degrees of freedom is 2.03. I'm making that up, but let's say that's what it is. Let's say your T calculated came out to 2.03, and they're exactly the same. What that would be telling you is that you have exactly a 5% chance of being wrong if you reject the null hypothesis. That's the probability that you would get that big a difference between these two means if the null hypothesis were true. Only 5% chance of that happening, right? So you would be at exactly 5%. Now, if they're further apart than 2.03, as they are in this case, then the probability gets smaller, shrinks, gets smaller and smaller. In this case, the probability you would be wrong, the p-value or significance, as it's called in SPSS, is only about 1%. It's 0.011. That's the actual true probability. And so we could reject the null hypothesis just on the basis that we knew that we exceeded the critical value, but that would only tell us that there's less than 5% chance. But the p-value tells us not only that it's less than 5% chance of being wrong, but also that it's only about 1% chance of being wrong. So we have even stronger evidence by having the p-value available to us. So we accept or reject the null hypothesis. In this case, our t-value we calculated exceeded, it's 2.0, I guess, exceeds 2.0, so we reject the null hypothesis. And we conclude that the mean response time for cell phone users is significantly different, statistically significantly different than the control group. As it happens, it's greater. We didn't make that assumption in the beginning. We just said different, right? Just said that the difference was not zero. So that's where we stand with that. Let me pick this up. Play from current slide. Okay. Okay, cell phone, LEUs independent. One group use cell phone, separate group. Alternative design use the same subject for both. Bingo, there's our paired sample t-test, as we were describing. Reaction times are measured when the subjects perform the driving test without cell phones, and then again while using cell phones. Okay, so let's take a look at it here. So for student number 1, see there's all our students there. Where'd it go? Okay, so for student number 1, right? No cell phone, 604, cell phone, 636. There was a difference of 32 milliseconds, 67 milliseconds. This person was faster with the cell phone than he was without the cell phone, came up negative, right? So now we do is we take, where'd it go? Here we go. We take all of the differences and we look at the differences as new data. The difference now is our real data. We're going to take the average of all the differences. And we take the average of all of the differences, right? Our expectation is if there's no, if it doesn't matter whether he was using the cell phone or not using the cell phone, then the average difference would be zero. So what we're testing here for is whether the difference, D bar, D with a bar on top of it, whether the average difference is equal to zero or not equal to zero. That's our null and our alternative hypothesis now. To compare the means, use paired differences for each paired. D is the reaction time, the difference. We can use either Z or T depending on the sample size, right? If sample size is really big, we might just go with Z. Right? So really big meaning over 100. Okay, so choose the appropriate test, paired sample t-test. Choose your level of certainty, 0.05. Alpha is 0.05, your alpha. Write the null and alternative hypothesis. The average difference is equal to zero. Sometimes you'll see that written as a D, uh, 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 with just a D and equals zero, or D does not equal zero instead of mean D and mean D there. Okay, but that works too. Okay, so we're going to take the difference between the average number of milliseconds and zero. Well, the average is going to be the difference between the difference is going to be 50.6 seconds, the average difference, minus what you're comparing it to, the mean you're comparing it to, which is zero. So it's just 50.6 on the top because it's 50.6 minus zero. The difference from the mean, difference from your sample versus the difference you're projecting, which is zero. Okay, so it comes out to be 50.6 on the top, and on the bottom you put your standard error. And your standard error is based on the standard deviation of your sample, your differences, which is 52.5, divided by the square root of your sample size, which happened to be 32. So that's your standard error on the bottom. Not complicated because you only have a single sample. You don't have two samples, two different sample sizes, two different standard deviations. Okay, so your degrees of freedom is 31. Turns out that, and you calculate t to be equal to 5.46. That's very big T, right? So now you go over to your table and you look up what is the t value that you need to exceed for a degrees of freedom equals 31, and it looks like it is around 2.04, right? So certainly our 5.46 exceeds that by far, so we can reject the null hypothesis. Okay, you can also calculate a confidence interval, right, by using x bar, the average difference plus or minus t for 5%, t for 5% at 2.03 times the standard error, which we calculated up here. There's your margin of error to add and subtract it from there. You can find that, and let me find it here. Did they do it? Did they bother to do it? You can calculate that confidence interval, right? And what will be expected? 95% confidence interval turns out to be 32 to 70. And notice that zero is outside of that confidence interval. We're 95% certain that the true mean difference is between 32 and 70 milliseconds, which means that we're 95% sure it's not zero because zero is outside of that range. So you kind of use the confidence interval there. Now, keep in mind that we can use, when we have a single sample test, it's not that uncommon to maybe look at it as comparing it to the confidence interval. When we use a t-test, we usually rely on a hypothesis test rather than looking for overlap or no overlap in confidence intervals between the two groups. Long story short, use a t-test, always, not confidence intervals for comparison when you're looking to reject a null hypothesis with independent samples t-tests. Okay, okay, good. So, all right, so this is a summary of the sample procedures that we just did. Okay, and over here to say proportions are not covered in this course. You know, I got kind of, I think the way I've been working on the schedule, updating the syllabus and the schedule, I think we might be able to squeeze in a little bit on how to do this with proportions. Compare, for instance, if you know that 50% of this population is susceptible to COVID, and you take a sample from another you had 50% of this population has had COVID versus this other population where 46% has had COVID, and you want to know whether those two proportions are really different for the entire populations that they came from, right? You can do the same thing. You can do a t-test between two proportions, just like you can between two means. That says not covered here, but we can kind of take a look at that at maybe that last part of the semester. So we don't have to get confused by it right now. Okay, so that's our summary. You can go back over the summary. Limitations of significant tests. Sample size is very small. You can have large different deviations from null hypothesis. So there's a lot of variability in there. So you have to really carefully design these studies. Okay. But when the sample size is very large, tiny deviations may be found to be statistically significant. What does that mean? That means if I take a sample of two groups, let's say people who drink one glass of wine a day and people who don't drink any wine a day on days. And I want to compare their blood pressures. And I take 1,000 people that drink wine and 1,000 people who don't drink wine. Well, let's say the blood pressures of these two groups. One group, the blood pressure is 89, and the other group, the blood pressure is 90. That the size of the sample is so large that it may be possible for me to statistically say that there's a statistical difference, there's 95% certainty that one group is mean is more than mean blood pressure, is higher than the other group's mean blood pressure, uh, and reject the null hypothesis. But clinically, it has no significance. It doesn't mean anything, right? There's really no difference between a blood pressure 89 and 90, right? It's not clinically significant. So when you get a really big sample size, and this one they're looking at camera sales on eBay, right, where what the minimum bid might be, and you have a sample size of 340,000. Even the teeniest tiny difference in the listing price, is going to appear to be statistically significantly different. So just be careful that on one end of it, they have a lot of variability. The other end of it, it's easy to show a statistical difference, but it may not be a meaningful difference. Okay, so okay, let's see if there's anything else here important that we need to talk about. Okay, so we're going to talk about power in just a second. We're going to get to that. Okay, so the p-value is one of the reasons we don't say that we don't say if we fail to reject the null hypothesis, we never say that we accept if we fail to reject the null hypothesis, we don't say that we accept the null hypothesis, right? Because that p-value is only used to show the differences between the two groups. It's not evidence that the two groups are the same, right? So that p-value only means something in terms of probability of the two population means being different, not being the same. Okay, so don't fall into that trap of saying instead of saying we fail to reject the null hypothesis, we accept the null hypothesis. Don't say we accept the null hypothesis ever. Okay, and okay, 0.05 is common cutoff point. There's no that 0.05 is arbitrary. The p-value really makes more sense. It really gives you a bit more information about your level of certainty that these two population means are different from one another, right? So if you look at if you get a p-value, if you get a p-value of 0.06 versus a p-value of 0.04, and you say, I'm going to reject the null hypothesis and completely change my conclusions about the differences between these two populations based on that little tiny difference, that doesn't make any sense. So even though we say 0.05 is kind of our cutoff, that's more of an academic thing than something in reality. Okay, if we really judge our level of certainty by that p-value, we may want to exceed 0.05, that level of certainty, but it's really the p-value is the level of evidence that we have that the two means are different. And so you can't look at it as, a yes or a no, right? So it used to be, fortunately, people have stopped asking me this, and that is that like, Tony, what do I do if the p-value, if the p-value is exactly 0.05? Do I reject or do I fail to reject? Right? So nobody asked me that. Hopefully, you'll never ask me that. right? Because it doesn't make, it's still 0.05, so it doesn't really make any difference. You could, on a test, I will certainly not make it come out to 0.05, so you're stuck struggling with that conundrum. Right? So at any rate, so yeah, so that's where we stand with this. Let me just pop through the rest of these. Yeah, study design critical. We had a little bit of on study design earlier. Now this one, this I don't know if I can blow that up while it's in PowerPoint. The other thing is that if you run a test often enough, you're going to get the result you want. Remember, we said that we're willing to accept 5% chance of being wrong. In other words, being wrong one out of 20 times. Rejecting the null hypothesis when we shouldn't. So here's a cartoon. Here's a study. We found a link. It's a study that says we found jelly beans cause acne. We found no link between jelly beans and acne. P greater than that settles out of here. It's only one certain color that causes it. So now somebody goes back and says, okay, let's test every color, right? So this person tests gray, this person tests, tan, this person tests cyan, this person tests this, and one person tests green jelly beans, and just his luck, they test 10 different colors. Now, all of a sudden, instead of having a 5% chance of rejecting null hypothesis when you shouldn't, you now have multiplied your chance of rejecting it. And sure enough, you test 20 different color jelly beans. You wouldn't be surprised to find that one time you'll reject the null hypothesis in error, right? So don't get lulled into repeatedly doing uh, uh, tests on slightly different things until you get the result that you want.